All right, in this video, we're going to cover section 3.6 on marginals, differentials, and linearization. So these are just some other applications of things that we can figure out using derivatives. So our objectives for this section: find marginal cost, revenue, and profit, and understand what those mean. Find delta y and dy, which we'll talk about that when we get there. That'll make a little bit more sense later. Use differentials for approximations, and find the linearization of a function at x equals a. The word linearization is just another word for equation of a tangent line. So we've talked about that already, so we're just going to be revisiting that topic here. All right, so our definitions for marginal cost, revenue, and profit. Let C of x, R of x, and P of x represent respectively the total cost, revenue, and profit from the production and sale of x items. The marginal cost at x, given by the first derivative C prime of x, is the approximate cost of the x plus first item. So the cost of just the x plus first item is approximated by finding C prime of x. So C prime of x would be approximately equal to, this is the actual cost of the x plus first item, the cost of x plus one items altogether, minus the cost of just the first x, leaves you just C, the cost of just the x plus first. So rearranging this equation, they've just added the C of x to both sides, getting C of x plus 1 equals C of x plus C prime of x. Marginal revenue, same definition, only using your revenue function. Marginal revenue is R prime, approximate revenue from the x plus first item. So R prime is R of x plus 1 items, or the revenue for the first x plus 1 minus the revenue from the first x is just the revenue from the x plus first. And again, you could rearrange this to say that the revenue for x plus 1 items is the revenue of the first x items plus R prime, which would be the x plus first. And then marginal profit, again, the same. P prime, first derivative of P, is the approximate profit from x plus first item, meaning marginal profit. So again, P prime is P of x plus 1 minus P of x. So the profit of all the first x plus 1 minus the profit of up to x leaves you just the profit of the x plus first. So this is profit of x plus 1 items is the profit up to the x item plus the profit of the x plus first item. All right, so anytime they say marginal anything, they mean first derivative, and it's the cost or revenue or product or profit, whatever you're talking about, of producing the x plus first. All right, so if we're given the cost function and a revenue function, they want to find each of the following. Total profit, P of x. Total cost, revenue, and profit from production and sale of 50 units. The marginal cost, revenue, and profit when 50 units are produced and sold. All right, so first we're going to find total profit using our cost and revenue. Then we're going to plug in 50 into all of those functions to get the total cost, revenue, and profit of the sale and production of 50 units, and then we'll find marginal values for all of those. In other words, the cost of the 51st, revenue of the 51st, profit of the 51st. All right, so profit is revenue minus cost. What you bring in from revenue minus the costs that you have to pay. All right. So revenue function minus the cost function that we were given. Don't forget to put the parentheses around cost so you can distribute the negative. Distributing the negative and cleaning that up gives me x cubed minus 74x squared plus 40x minus 27,490. Part B, taking the cost function at 50 units gives me $182,500. Revenue function for 50 units, $97,010, and the profit function for 50 units, negative $85,490. So that's just the cost, revenue, and profit of producing 50 items. All right, C prime is the first derivative of cost. C prime of 50, 6,200. So the cost of producing the 51st item is $6,200. Revenue, R prime, marginal revenue. This is the derivative of the revenue function. Evaluating it at 50, $63,040. So the revenue taken in for the 51st item, $63,40. Profit function's derivative is this. Plugging a 50 into that is $140. So the profit for the 51st item is $140, which makes sense because $140 is the difference between revenue and cost. So when 50 units have been made, the approximate cost of the 51st item will be $6,200. The approximate revenue from the sale of the 51st is the $63.40, and the approximate profit on that 51st item is $140. All right. Next example is just given a random function, y equals x squared, a value of x, and then delta x value, and they want you to find the delta y. So basically they're saying find if this function has an x value of 4, but you changed it to be 4.1, right, meaning that you're going to move over 0.1 for the change in x, what would the change in y be? All right, so the change in y, delta y, is f of x plus delta x, so starting at 4, moving over 0.1, subtracting the original value of f of x. So that's how we calculate delta y. All right, so we're given 4 for x, 0.1 for delta x, and we're plugging the 4 plus 0.1 into f. So the f of x is the x squared, so that's this thing plugged into the function, meaning that thing squared, minus f of x, meaning f of 4, so 4 squared. That's 4.1 squared minus 4 squared, 16.81 minus 16, or 0.81. So in other words, when x changes by 0.1 from being x equals 4, y changes by 0.81. All right, so let's try another one. For y equals 2x to the 4th plus x, if x is 2 and it changes by negative 0.05, meaning it decreases, find delta y. All right, so delta y, f of x plus delta x minus f of x again. That'll be our formula. So we're plugging in our x was 2, our delta x was negative 0.05. So 2 minus 0.05 is your x, so it's 2 minus 0.05 to the 4th plus 2 minus 0.05. That's what it would be if I plugged it into my function. Minus f of x was 2, so just plug 2 into the function. Clean it up with your calculator. Should give you negative 3.1319875. So in other words, for this function, when x changes by negative 0.05, y changes by negative 3.1319875. So a very slight change in x, right? We're figuring out what the change in y effect would be. All right, for f, a continuous differentiable function and a small delta x, we can approximate this using our f prime definition. So the derivative f prime of x is approximately delta y over delta x, change in y over change in x, over slope of the tangent line. So if I rearrange this equation and solve it for delta y, multiply both sides by delta x, we get delta y would be approximately equal to f prime times delta x. All right, so let me go back here real quick. So to calculate delta y approximately, we can take the derivative of f and plug in our x to the derivative and then multiply it by the delta x value. In the last few examples, we were calculating the exact value of delta y. This is a way of approximating delta y. So they should be close, but not exactly the same if I compared the two methods. All right, so we're going to approximate the square root of 27 using that definition. Okay, so I know your calculator just gives you an answer when you ask it to do this, but it's giving you a decimal, so that's an approximated value. All right, so one way to do this. Let f of x be the square root of x, because this is the square root function of some number. And x, we're going to pick a number close to 27, but we want a number that's easy to find the square root of. So we're going to pick 25. So pick the closest number to 27 that you can that is a perfect square root. So 25. So since choosing 25 would allow this to be simplified easily, that would tell me that delta x is 2 because 25 and 27, they're 2 units apart, the change in x. All right, so f prime, my function was the square root of x, so we're doing a square root of a number. My first derivative, you first would write this as x to the 1/2, so you'd get 1/2 x to the negative 1/2, and then bringing it to the bottom as a positive 1/2 as a square root on the bottom. All right, delta y is f prime of our x times our delta x. All right, so here's my f prime. Our x, we said was going to be 25, and then our delta x is 2. So plugging a 25 into here, this is 5 times 2. Actually, your 2's end up canceling here. And then this is 5 on the bottom, so 1/5 is 2/10 as a decimal. So delta y would be 0.2. Now you can approximate the square root of 27. The square root of 27 is approximately the square root of 25, because we used 25, right, initially as our x, plus what we got for our delta y. So the square root of 25 is 5. Our change in y was the 0.2. So if I add 2 to 0.5, the square root of 27 is about 5.2. Okay, let's try another one. Approximate the square root of 98 using the same method. To 5 decimal places, the square root of 98 on your calculator is this decimal. They want to know how close is that approximation. All right, so again, we're going to use the square root of x as our function because we're square rooting a number. And we're going to pick a number for x that's close to 98, but that you can do the square root of easily. So we're going to use a 100 here. The square root of 100 is a perfect square. It's a perfect, like, is a nice answer. So this time, if I pick 100 as my x, I want to pick something close to 98. I want to pick 25 again because it's nowhere near 98, and that won't work. So picking 100, my delta x then would be -2. In other words, to get from what you picked back to what you're going to eventually plug in, you have to subtract 2. On the other one, we were going to plug in 27, but we chose 25, so we would have to add 2. So this time at delta x is -2. So again, my derivative of my function f. Delta y is the derivative evaluated at my x choice, so plugging in 100 and multiplying it by my delta x value. So plugging in 100 into this, then multiplying it by -2, gives me -0.1 as the change in y. So the square root of 98 is approximately the square root of 100. That's what we used to estimate, plus my change in y value that I calculated. So that's 10 minus the 0.1 from the delta y, or 9.9. So it's within 0.001. All right, sorry about the phone call there. All right, so this number, 9.9, is within 0.001 of the actual value. If you did that on your calculator and you got the decimal, this is what we got, just as an approximated value, so that is very, very close. Okay, so if I took the calculator decimal, subtracting what I got, we're within 0.001, or 1/1000th. It's just a way to estimate numbers like that without needing the calculator. All right, next here is a definition of what we call differentials. So for y equals f of x, we define dx, called the differential of x, by dx being the same as delta x, okay, the change in x. dy, called the differential of y, we find by that formula. dy would equal f prime of x times dx. Remember how we did delta y equals f prime times delta x? We're just plugging in our delta x using a dx, the differential. So if we use the d notation with dx or dy, it's just called a differential. of that variable. In other words, how it changes. All right, so for this function, y equals x times 4 minus x to the third, we would like to find the dy differential. Find dy when x is 5 and dx is 0.2. All right, so we're going to use our definition from the last slide to do part A. All right, so first, and one way to do that is just to use what you know about that you're finding a derivative. So dy over dx, we're going to have to use the product rule here. So the first function is x times the derivative of the second. So that's 3 comes down. This stays to the second times the inside derivative, which is -1, plus this is the second function times the derivative of the first. The derivative of the first function is 1. So it's knowing to use the product rule. Also, you're using the chain rule on the second piece. All right, so here they factored out a 4 minus x squared from both of these. So taking out 4 minus x squared here leaves me the -3x right here, plus, and then taking out a 4 minus x squared here leaves me a 4 minus x to the first, which is just 4 minus x. They just factored there. Cleaned up the second term. From the second term, they factored out a -4, so this just stayed. -4 got factored out here, leaving x minus 1. So remember, this line right here is equal to dy over dx, which means dy, if I just think of this notation as dy over dx, just multiply both sides by dx, and that's your formula. Dy equals the f prime times dx. All right, so now we just can plug in what we were given. We were asked to evaluate that for an x value of 5 and a dx value of 0.2. So we're going to plug in 5 for the x's and 0.2 for the dx. So x value would be 5. Hold on one second here. This should have been a 5 minus 1. They plugged in a 4. So 4 minus 5 and 5 minus 1 should be there. They made a mistake here. Yeah, this should be a 5 minus 1. So you'll have to check. I don't know if that number comes from plugging in the 4 or the 5, but this number right here should have been a 5 because that should have been a replacement for x. Anyway, cleaning that up is your answer. So if that's the right answer possibly, or this might need to be actually a 5 instead of a 4 to get a different number there. Okay, -3.2. All right, so let y equal f of x be differentiable at a. Then what we call the linearization of f at a is given by this equation. Okay, this is just the same thing as the equation of a tangent line at a point, just written in a different form. So y equals the y value, f of a, plus f prime of a times x minus a. It is the equation of the tangent line to f at a. So we take the derivative of the function, we plug in a, that's our slope. So this is slope times x minus your x value. And then if I had this on the other side, it would be y minus the y value equals slope x minus x. So that's the same thing as your point slope equation. All right, so find the linearization of f of x equals the cube root of x at a equals 27. Okay, so we're at the equation of the tangent line for the cube root of x at a equals 27. Then we're going to use it to approximate the cube root of 28. So you could approximate those values also by using a linearization method. All right, to construct the linearization, we need to find both f of a and f prime, given the value of a. So f of a, plugging in 27 into my function, is 3. F prime of a, first do f prime of x. So f prime, this would be x to the 1/3, so you'd get 1/3 x to the -2/3 by your power rule. This would move to the denominator as a positive 2/3, which is the same as the cubed root of x squared. Then we're going to plug in 27 into that, and that gives me 1 over 27. So the linearization of f at 27 is the equation of the tangent line at x equals 27. Remember, it was this. So we got 3 for f of a. We got 1 over 27 for f prime of a, and then a was 27. So they're just plugging in what we got. along with our a value into that equation. If you distribute the 1 over 27 and clean it up, you'll get y equals 1/27 x plus 2. Or you can call that L of x. Either y equals that or L of x equals that. All right, so if I want to then approximate the cubed root of 28, all you need to do, if you found your linearization function, is just plug a 28 in here. So plug 28 into your equation of the tangent line. 28 over 27 plus 2, 82 over 27. So on your calculator, well, so first of all, the cube root of 28 is approximately equal to what we got here, 82 over 27, which is this decimal, 3.037, all that repeats. On a calculator, if you just asked it to do the cube root of 28, you get 3.0365. So very close. This would round, if you rounded to the nearest thousandth, they would round almost to be the same thing. All right, so the summary here. Cost represents cost of producing X items, then marginal cost is its derivative, which is the cost of producing the X plus first item. If revenue is the R of X function, marginal revenue is the first derivative, represents the revenue from producing the X plus first item. And profit is if P is your profit function, marginal profit is the first derivative, and it is the profit from selling the X plus first item. Okay, in general, profit is revenue minus cost. We've used that before. Using the delta notation, delta X is the change in X, so it's the X plus H value minus the X value, which is basically H if you think about our original definition of derivative. It's the change in X. Delta Y is f of x plus h minus f of x, how the y values change when you change by the value delta x or h. For small values of delta x, dy delta y over delta x equals f prime, which is equivalent to multiplying both sides by dx, this. Using differential notation, the differential of x is dx. And since dy over dx equals f prime, we could write that as dy equals f prime times dx. So if you're calculating a dy value, it's the derivative evaluated at x times the change in x. So in general, the dy is approximately the same as delta y, and the approximation can be very close if your x's are, or if your delta x values are very small. All right, so that is the end of section 3.6.